with the proof of the theorem. Okay? Let's start with the proof of the theorem. For the sake of simplicity, I'm going to call this matrix X minus Xi minus A as the matrix B. Then obviously the characteristic polynomial of the matrix A is going to be the determinant of the matrix B actually. Okay? By the way, we know one identity about the determinants and the matrices is this actually. Let me recall quickly something interesting. How do you compute the inverse of a matrix? There are several ways of it, but you can calculate it through adjugate or adjoint of the matrix actually. So we know that it's adjoint of the matrix B divided by the determinant of the matrix B actually. Okay? And if this is the case, and I take B times B inverse, this is going to give me identity. So if I substitute, for example, the value of B here, so this is going to be the adjoint of B divided by the determinant of B times identity matrix. Now B is going to be the adjoint of B equal to determinant of B times I. Okay, this is what that identity that you're gonna probably I was about to write it kind of directly, but you can drive it very easily. That for any given matrix B, if you multiply it with its adjoint, this is same as multiplying the determinant with the identity matrix actually. Okay. Now I would like to make you make you realize something. What is the degree of this polynomial? This polynomial is the characteristic polynomial. And the characteristic polynomial is an nth degree polynomial because A is an nth degree matrix. So it's going to be a polynomial of this form, C0 plus C1 x plus so on and so forth, Cn x power n is going to be something like this. Okay, so this means that determinant of B is an nth degree polynomial. What is going to be the polynomials in the matrix B actually? So when you compute, for example, B, okay, when you compute, for example, B, what kind of terms will appear actually? So it's going to be, x minus a11 and something, and you're going to have x minus a1, a22, so on and so forth, x minus a and n. So you're going to get something like this. So there are going to be some entries here and some entries here in upper and lower diagonal. So at the diagonal of this matrix B, you have the linear expressions. Okay? You have these linear expressions. So in other words, in this matrix you have polynomials of 1 degree, and this is the degree n degree polynomial. So what would be the polynomials of degree in the adjoint matrix B? So it must be at most n minus 1 degree polynomial. It would be at most n minus 1 degree polynomial, because when 1 degree polynomial will be multiplied with n minus 1 degree polynomial would give you n degree polynomials on the other side actually. Are you getting the point? Okay. So in adjoint of the B, you're going to have n degree polynomials sitting inside. So if this is the case, then how does the adjoint of the B would look like? By the way, what would be the order of the matrix adjoint of B? It's going to be an n by n matrix. Okay? So the adjoint of the matrix B is going to be some people also like to call it adjugate matrix actually, okay? So adjugate matrix, it doesn't matter. So we call it adjugate or adjoint, doesn't matter, okay? I hope you understood. Determinant of B is going to be the polynomial, okay, with n degree. So this means that this is a matrix in which the entries are nth degree polynomial. What is the degree of polynomial in matrix B? So it's first degree polynomial. So in order to be the nth degree polynomial on this side, the adjugate matrix must contain at most n minus 1 degree polynomial, because n minus 1 degree polynomial when multiplied with 1 degree polynomial can give you nth degree polynomial. So the adjoint of B is going to consist of, it's going to be an n minus n matrix, but in this you're going to have some polynomials that has degree and at most n minus 1. So let's call those polynomials P11 of x up to P1n of x up to Pn1 of x up to Pnn of x. This is how explicitly this adjoint matrix is going to look like, where each Pij of x has either exactly equal to n minus 1 degree or less than n minus 1 degree, has at most is at most n minus 1 degree polynomial. Okay, it's going to be at most n minus 1 degree polynomial actually. So if it is at most n minus 1 degree polynomial, so how does I can write this actually? How can I write the adjoint of B kind of more explicitly? I can write adjoint of B more explicitly. Okay. Let me show you one example, that if I have a matrix, if in a matrix I have written some polynomials, say for example I have like this x squared plus x plus 1 and x minus 1 and say x, and I have 2 x plus 1 3 and say x square minus 1 and x square minus 1. For example, you have this matrix in which you have second degree polynomials. I can write this polynomial. Before writing an expression for this, I just like to give you a kind of a demonstration that imagine you have a 3 by 3 matrix in which each entry is at most 1 degree polynomial. Then I can write this matrix in the form of a matrix polynomial actually. What would be that? How can I write it? I can write this as what? Say for example, I write x square, okay? I write x square and take the coefficient from here 1, 0, 0, 0. Why 0? Because there is no x square here, there is no x square here, there is no x square, there is no x square, there is no x square, there is x square, so I'm going to write 1. So for example, if there is a 2, so the matrix coefficient of x square is going to be 1, 0, 0, okay? And 0, 0, 0, and say 1, 0, and 2 actually, okay? So when I multiply this, I'm going to get x square 0, 0, 0, 0, x square 0, 2x square. Plus, I can say I have x. Now I can take, all, entries in which the x is there actually. So it's going to be 1, it's going to be 1, 1, 1. There is no x in the second quantity, 0. I can write 1, 0, 0, 0, and 0. Okay? And plus, the matrix of the constants. Okay, matrix of the constants. So it's going to be 1, -1, 0 because there is no constant there, 3 or 2, whatever, 2, 1, 3, 0, -1 and -1. Now, if I have a 3 by 3 matrix of 2-degree polynomials, I can write this in the terms of a polynomial in which the coefficients are matrices actually. I can say that this is same as b2x square plus b1x plus b0, where b0 is this matrix, b1 is this matrix, and b2 is this matrix actually. Okay, so I can play this trick to write this polynomial. Now, if, so here's the interesting thing, if adjoint of B comprises of n-degree polynomials actually, okay, it comprises of n-degree polynomials, then I can also write it in, the matrix form as I just mentioned. So it's going to look like something like this. A B0 matrix consisting of all constants from here, plus a matrix B1 that consists of all coefficients of linear degree polynomial, plus so on and so forth, and Bn-1 consisting of all coefficients of n-1 degree terms, x power n-1. Okay, so that's how this adjoint of B is going to be the matrix polynomial, where, by the way, all of these B0, B1, where all of these B0, B1 up to Bn-1 are n by n matrices. Okay, they are n by n matrices actually. Now I would like to use this identity. Okay, this interesting identity. Let's use it. The determinant of Bi for the determinant of B multiplied with the matrix I, okay, which is equal to what? B multiplied by the adjoint matrix of B. But matrix B is xi minus A times adjoint matrix of B. So if this is the case, what you're going to get? You're going to get determinant of B multiplied by I. So if I take this matrix and multiply with each term, I'm going to get x multiplied with the adjoint matrix of B minus A multiplied with the adjoint matrix of B. Okay, that's what we're going to get. Now let's compute what would be the determinant of, by the way, matrix B multiplied with the matrix I. Okay, determinant of the matrix B multiplied with the matrix I actually. The determinant of the matrix B is this polynomial. What is this polynomial? C0 plus C1x plus so on and so forth, Cn x power n multiplied with this matrix I, which is what? 1 0 0 0 0 1 0 0 0 0 0 and 1 actually. Okay, this is what that you're going to get. So it's an n by n matrix. So what this matrix would explicitly look like? This matrix would look like that this polynomial is sitting at the diagonal terms of each term. So it's going to be C0 plus C1x plus so on and so forth, Cn x power n 0, 0, and then 0 again C naught plus C1 x plus so on and so forth, Cn x power n, so on and so forth, 0, and so on and so forth, 0, 0, 0, 0, and last term is going to be C naught plus C1 x plus Cn x power n actually. Okay, this is what that you're going to get. Now, if I play the same game that I play with the adjoint, in other words, try to write this in the terms of what do you call a matrix actually. Okay? Now, let's compute this. If I write this in the terms of matrix, so the first thing that is going to be that, okay, take C naught, in other words, take the terms with the constants and rest of the terms, so it's going to be C naught 1 0 0 0 0 1 0 0 0 so on and so forth. So it's going to be C naught matrix I. So this matrix is going to contain C naught 0 0 0 0 C naught 0 0 0 so on and so forth. How about the second term? So from the second term, if I write C1x multiplied with the matrix I, C1x multiplied with the matrix I, so this is going to be what? C1x 0 0 0 0 C1x 0 0 0 and so on and so forth. And similarly, what I can do, I can take for example these last coefficient and I can say Cn x power n multiplied with the matrix, what do you call I actually, okay, multiplied with the matrix I. So once you have this, what you're going to get. So in other words, I wrote this matrix in the terms of a polynomial. Now I have an explicit expression for this polynomial. In other words, this side of the identity, this side of the identity, and I have also a polynomial for this side of the identity, and let's compare both actually. Let's compare both and let's see what you get. Let's see what you get. So let me use this polynomial on the place of this, determinant of b multiplied by I. So on one side I'm going to get C naught I plus C1 x I plus so on and so forth, Cn x power n I. On other side I have x adjoint of b minus a multiplied by adjoint of b actually. This is what that you're going to get. Now what is the expression for adjoint of b? It's this polynomial. So let's multiply this with x. So what you're going to get? I'm going to get b naught x plus b1 x square plus so on and so forth, bn minus 1 x power n actually. This is what that it is going to be. Minus, now if I multiply this a with each one of these terms, so it's going to be minus ab naught minus ab1 x and so on and so forth minus abn minus 1 x power n minus 1. Okay, this is what that you're going to get. Now, if I combine the terms, like combine the all terms with x, combine the all terms with y, with x square and so on and so forth. So the term without polynomial degree, without variable is minus ab naught, okay, plus I'm going to get b naught minus ab1 times x plus so on and so forth. The last term is really, or the second last term with this, so if this is the term, what would be the second last term? The second last term is going to be bn minus 2 x power n minus 1. Okay? So this term will be added with this term, so you're going to get bn minus 2 minus abn minus 1 times x power n minus 1, and plus last term is bn minus 1 x power n. Okay. Now let's compare the coefficients. Okay. Now we're going to compare the coefficients. On one side I have this, and on the other side I have this actually. Let's make the comparison of the coefficients. So what are you going to get? You're going to get this actually. So the first thing is minus AB naught is C naught I. Okay. Minus AB naught is C naught I. This is first equation. C1I is B naught minus AB1. Okay. C2I is what? So if it is B naught minus AB1, so it's going to be B1 minus AB2. Yes. So it's going to be B2 minus AB1. B2 minus AB1. Now, this is going to be B1 minus AB2. Okay, because I'm doing the proof a little bit different from notes. So the second last term is going to be Cn minus 1 I equal to what? Bn minus 2 minus Abn minus 1. Okay, and the last term is Cn I is really what do you call minus or plus Bn minus 1. So this is what that you're going to get. Now let's do the a bit more clever calculation actually. Okay.